Time is up. Good afternoon, everyone. My name is Fan Zhenxiu. I'm the session chair. Our first speaker is Professor Bulatov from Simon Fraser University. His research interests are constraint problems, computational complexity, and combinatorics. The title of his talk is Hard and Easy Constraint Problems. Let's welcome Professor Bulatov.
Okay. Good afternoon. Thank you very much for having me here and for coming for my talk. Well, I'm going to talk mainly about this constraint satisfaction problem. More people are going to talk about constraint problems. So tomorrow we will have Dmitry, who will be talking about similar things, hopefully in more details than I'm going to do today. And also in the morning tomorrow, we will have Venkat Guruswamy, who will give apparently his boss view on the area. Okay, so I'll start with trying to convince you that whatever you do constraint satisfaction. So, during COVID, this way. During COVID, of course, everything was online. Well, I would come to the department like once in a while, and we had a guard sitting right by the door. And I very soon recognized him as my colleague because he was reading this book, or rather working through this book. So after a while, after a month or so, maybe a couple of months, he apparently finished the book and started to do this one. After a few more months, he changed the books again, and then COVID stopped. So he never got to this point, believe you or not. Anyway, so my point is that, Sudoku, as we know it, is one of the examples of the problem that I'm going to talk about. In reality, this and this is the same problem in a way, or at least they fall into the same framework. Why is it so? So what do we need to do in Sudoku? Well, of course, we need to fill all these cells with numbers in such a way that all numbers are locally different, right? So they're different in every row, every column, every block here, so locally. And same with the system of equations. We need to assign values to those variables, indeterminates in the equations, in such a way that every single equation, local equation, is satisfied. So in both cases, what we need to do is to solve a constraint satisfaction problem, which is to say that we want to assign values to some variables, to cells in this case, to indeterminates in this case, in such a way that we satisfy a bunch of local constraints. So local constraint here would be, all values are different in every row, column, and block. Constraints here would be, satisfaction of every single equation. So a constraint there, everything is different in the block. A constraint here is an equation. Okay, so let's do it a little bit more formally. So that's what I'm going to do. I'm going to introduce a formal definition of the CSP, constraint satisfaction problem. And it goes like this. We are given a bunch of variables, as in those examples from before. What we want to do, we are given constraints. They can be defined. I will give some examples. They can be defined in multiple ways. But overall, it's some condition that in the most general form we may think as just a bunch of combinations of values. Right, that's the most general representation. How we do it in reality varies. Again, we'll see some examples. Right, what we want to do, we want to find a solution such that, so assignments to variables such that all constraints are satisfied. Okay, so that's our problem we are going to talk about. All right, so where did it start? It started surprisingly with computer vision, or more precisely in the 70s, Montanari tried to develop basically this framework to reconstruct 3D scenes from a picture or from some image anyway. So what can we see on an image? Well, we would see something like this, of course. And well, we are trying to reconstruct how these objects, like this cupboard and this cutout man, are actually located in the space. And of course, we would conclude that, well, if we look from above, they look something like this. Well, this is us looking at them. So the picture should be like this. Okay, so for two of them, and we conclude that if we see something like this, that the man is behind the cupboard. So that's a constraint, a relation. One object is behind another object. So suppose now we have multiple objects, and we can figure out such relations between them. How can we place them in this area, room, or whatever, so that it matches what we see? So that was the first application of this formal constraint satisfaction problem. Okay, I guess now people do it in a slightly different way, but anyway, that was the first idea. Okay, more examples. I mentioned equations. So system of linear equations is a CSP. Of course, every relation is a constraint. Well, if you imagine a sparse matrix, right, very sparse matrix, then every constraint is real kind of local because it corresponds only to those non-zero coefficients and things. I will mainly talk about finite domains here. So generally, I would assume that that values for variables here come from some finite set. So I'm not quite sure what 1.5 is doing here, but anyway, the idea is still the same. So in the system, well, we of course need to verify if it's consistent. And the relations we have here would be combinations of values that can be represented by linear equations. Right, so, okay. Well, another one, a very famous and profound problem, which is satisfiability. I'll talk about, well, a restricted form of satisfiability, 3-SAT. So what do we have there? In satisfiability, we have this input, which is a CNF, right, a logic formula, a conjunctive normal form. So it consists of clauses like this. 3 means that you always have 3 literals in every clause. What we want to do is to check whether it's satisfiable or not. Famous problem, the first to be proved to be NP complete, and all this stuff. So where are constraints? Where is everything? Well, obviously these are variables, right? Obviously we assign values 0, 1, no problem. Then every clause is a constraint, right? And conjunction means that we want to satisfy them all. So that's basically, again, a CSP, okay? If you like graphs, as I do, then K-coloring, well, would be your favorite example of a CSP. Say, what do we want to do? Well, we are given the graph like this, and we want to color every vertex in such a way that adjacent vertices get different colors. Right? That's graph color, K-coloring, K different colors. Again, how can we think about it as a CSP? Well, the variables here are, of course, vertices, right? These are something that we assign value to. Okay, so the values are, of course, colors. We have K different values. And what about constraints? Well, the constraint is the colors on the ends of every edge have to be different. So in a way, the constraints would be this disequality relation, just demanding that the values here and here are different. Okay, so again, another CSP. Okay, something else. Well, that's another famous problem, or well, maybe less old, but still very important. I'll mention it later. Again, it looks pretty much like K-coloring, only again we are assigning values to vertices, sorry, and all this stuff. But instead of disequality, we impose some functions or bijections on the edges. So we demand that, for instance, that the value of this one can be computed from the value of this one. right? And again, what we want is to check if we can do that and so on. Okay. Something else. Scheduling, again, some AI problem. Well, that's if you want to schedule some tasks or whatever, what people often do is use so-called Allen's interval algebra for that. What is Allen's interval algebra? Suppose we have a bunch of tasks and we want to schedule them, right? Like place them on a real line, basically, right? But we have constraints. Say, for instance, we want to complete one task before we start the second one, and well, things like that. Okay, so they may precede one the other. They can meet. They can meet meaning like this, or they can overlap, and so on and so forth. So, for instance, if we have say 3 tasks, and from whatever we know about them, we want that x and y start at the same point. Z is completed during y, so it's kind of inside, and x precedes z. Then how we can place them, say this is x, then y clearly should be longer, something like this. Z should be, well, inside y, but it should be after x. Right? So that's basically the picture. Again, we have variables, right? Those tasks are variables. Values are a little bit more complicated. Values would be intervals. This is why it's interval algebra. Intervals on a real line, and these are constraints. A CSP again. A CSP again. Okay, so CSP is everywhere, in a way. So next I'll spend probably something like 15 minutes or so just talking about connection of CSP to other fields and why we like CSP, why we think it's important to do. So you may not be able to recognize kind of everything here, but most likely everyone will recognize something familiar in this list of friends of the CSP. Okay, so here is CSP. Friend number 1, again, for those who likes graphs and problems related to graphs, CSP is related to homomorphism problems. What is a homomorphism problem? Let's look again at k-coloring. I claim, well, or rather I define these things as follows, this problem as follows. I'm claiming that a k-coloring of a graph, this one, is the same as a homomorphism of this graph into k, okay, if it's k coloring kk, well, in this case it's k5, complete graph with 5 vertices. What is a homomorphism? A homomorphism is a mapping. I need to map every vertex here to a vertex here, right? In such a way that an edge, every edge, goes into an edge. Now, why is it exactly the same as k coloring? Well, I assign a color to every vertex, basically, right? In such a way that every edge gets different color. So that's exactly a homomorphism of one graph to another. Okay? So we can actually observe that's not that difficult, that this homomorphism problem is the same as CSP. So we can define it in a more general framework of relational structures rather than graphs. Well, relational structure simply means that in graphs we have one binary edge relation, right? In the relational structures we can have a lot of different relations, right? But if we think about graphs, that's okay. So it's equivalent to the CSP, and translation goes roughly like this. In the origin structure, elements are variables, so we map variables somewhere. Constraints, and tuples in the relation are constraints, the bunch of variables on which we impose a constraint. Okay, on the right-hand side, again, it's just elements are elements, and relations are just all those relations that we are trying to satisfy. Okay, say, people often use this term H coloring if in this homomorphism problem this one is fixed. So for instance, for k coloring of a graph, that would be kk coloring. Kk meaning complete graph with k vertices. Okay. All right. So why this framework may be convenient? Well, it allows for some flexibility. So for instance, suppose that I want to solve problem on some kind of graphs, like planar graphs. Well, we know that many problems are solvable easier on planar graphs. Then what we need to say is just, okay, we are going to use a CSP where the inputs, well, the left-hand side input is restricted to planar graphs. Feder-Vardi even introduced some terminology about this, that if we fix the right-hand side structure or graph, then, well, the hardness of solving the CSP he would call query complexity. I will explain in a minute why query. And data complexity would be if I restrict, for instance, my graphs to just planar graphs. Okay, just planar graphs. Okay, next one. Next connection is to databases. Okay, so where do databases appear here? Let's see. So what is a relational database? Well, it's basically just a bunch of relations, tables. Every table is a relation, right? It just consists of those tuples, right, organized in tables. Well, what do we want to do with databases? Well, we want to ask queries, of course. Okay, so to make a query, what do we need to do? We need to specify a logic formula. Give me all records that are like this, but not like that, and something else, or something else, something like this. So that would be a logic formula. So in databases, what we want to construct such a formula and request all the records that satisfy this formula, or all models of those formulas, right, in the database. A very important special case of queries are conjunctive queries. So if you Google things, what do you ask? Find me things that are this and this and this and this. Yeah, well, Google allows for more general queries, of course. But when did you try it last time? This more general query. So most often we use just conjunctive query. Find me all people who live in this area, work at that company, and so on and so on. Right? So that would this is what a conjunctive query would look like. The thing is, a conjunctive query is exactly a CSP. I want to satisfy all these relations. Or rather, I'm looking for all records that satisfy all these relations. So I want to find all solutions to a certain CSP. So any query to a database is a constraint satisfaction problem. Okay, but actually things go a little bit deeper than that. So a conjunctive query, it's a CSP and therefore it's a homomorphism problem. Very few people working in databases think about queries this way, but some do actually. And here is who think this way. So what I'm doing, well, I have a query, I'm kind of sending it to the database, and I'm trying to get all the answers. Now, a big area in databases is this query optimization, right? Some queries are easier to answer than others, obviously, right? So if I have some complicated query, can I kind of transform it somehow so that it's easier, faster to answer? That is what's known as query optimization. Well, again, we can introduce all these definitions. Say, suppose I have two conjunctive queries, right? I will say that one of them is contained in the other if every answer to the first one is also an answer to the second. So in some sense, this is a stricter one, right? So this, for instance, this one asks for people living in Beijing area. This one asks about people living in downtown Beijing, something like this, right? So this is a stricter one. And if I have two that are both contained in each other, they're equivalent. So the answers to them are equal, are the same. They have the same answers. But maybe one of them is easier to process. So what I would like to do, I would like to kind of, having this one, more complicated one, somehow transform it to get an easier one. How can I do that? Well, a classic theorem by Chandra Mellin says that one query is contained in the other if there is a homomorphism, if you look at queries as relational structures, there is a homomorphism from one to another. Query optimization is a CSP. Query optimization is a CSP again. Right? So there is another problem in databases that is related to CSPs. Okay, I probably skipped this part just to save a little bit of time. Okay, well, another one is again this area about, or rather problems that ask about some a restricted class of graphs, for instance, like planar graphs or something like this, the other side. Let me put it this way. Again, it will be clear why it is the other side. So suppose I have some class of structures, like planar graphs. Okay, think about it as planar graphs. And I want to solve my CSP only for planar graphs. Say, I want to color planar graphs. I want to look for, I don't know, Hamiltonian paths in planar graphs. I want to look for cliques in planar graphs and stuff like that. Right? Okay. It turns out that we know a lot about algorithms and complexity in this case. Say, for instance, we know that if boundarity means that we cannot have relations with very, very long tuples. Say, graphs would be boundarity. It's arity 2. It allows only binary relations. Well, for instance, we know that if it's solvable in polynomial time, then, well, if and only if this class has bounded tree width. So some very well-known and well-behaved behaving condition. So that's completely known. Actually, if you kind of dig deeper here, it's a really beautiful area because it has so many connections. You can express it through logic games, homomorphism, duality, well, many, many different ways. Really different, a lot of different ways. And, well, that's one of my favorite, actually. But unfortunately, it's all done. Nothing left to do, almost. Well, okay, say if we allow unbounded arity in this class, like structures with very long relations, then we have this funny condition called bounded fractional hypertree width, which I'm not going to explain, of course. But again, much is known about this case as well. Okay. So the next one is another interesting question. It's related to so-called descriptive complexity of problems. So we know this complexity class is P, NP, and things like that, right? Solvable in polynomial time, those whose solutions can be checked in polynomial times. Well, there are these claims that allow to express or rather characterize those complexity classes through logic formulas. So for instance, well, the famous theorem by Fagin says that a problem is in the class NP if and only if I can write a logic formula which is existential second order logic, right, such that the yes instances are exactly those that satisfy this formula. So for instance, how would I do that for, say, 3 coloring? Existential second order means that I can guess a set. So in this case, I would say, okay, I want to guess 3 sets. I want to guess a set of red vertices, a set of green vertices, and a set of blue vertices. Then I say, okay, I guess those sets, there are 1 set, 2nd set, 3rd set, such that, well, every vertex, if every pair of vertices, if they are connected by an edge, they belong to different sets. That would be an example of an existential second order logic. So I am allowed to guess a set, right? So that is for NP. We also know that if the famous problem about P not equal to NP has a positive solution, so that the 2 classes are different, there are infinitely many problems that are not reducible to each other between P and NP. Again, an interesting problem would be, say, we have this class NP. I want to kind of make it slightly smaller, say, restrict to problems of a certain kind, in such a way that I have so-called complexity dichotomy. that is, sorry, complexity dichotomy that is every problem from this large class is either polynomial time or NP complete, and nothing in between. No, this intermediate complexity occurs. Right? So how can I do that? Well, again, there have been attempts, say, Kuhn and Nesha-Trill tried all kinds of combinatorial conditions of this lifts, shadows, and stuff like this. Well, another approach is through logic. Again, Vardi with Feder invented this logic that we are, well, I don't have to sort of explain what it is. It's monotone, monadic, strict, NP, whatever it means. So it's this satisfying three extra conditions. And they showed, for instance, if you drop any of the three conditions, that the resulting logic allows to express the whole NP, right? But if you introduce all of them, then what you get is the CSP. So in a way, they show that the CSP is the largest class that is not the whole NP. So that's sort of this abstract relation well, shows up here in this area as well. Well, another area is, again, well, the hope for descriptive complexity was that if we find the logic that we use for NP, say for NP we have this existential second order, maybe we can find a logic for P. Then we might be able to prove that P doesn't equal NP. If the logics are different, what we need to do, we need to find a problem that is expressible in the stronger logic, but not expressible in the weaker logic. And that's basically some kind of combinatorial stuff, hopefully. The problem is we failed to find a logic for the class P. So first order logic is very weak. It cannot express much. If we add, least fixed point operator, it basically just means that we can starting with a binary relation, we can take the transitive closure of the binary relation. That's basically all it is. Then things are interesting because Immerman and Vardi proved that this LFP of O expresses all problems in P as long as we have an order on them. So for instance, if you start with a string of letters, right, there is a natural order on the string. Then this is what describes the class P on strings. But if you have something unordered, like a graph, for instance, there is no natural order, so it doesn't fall into this category. Okay. Well, the problem that we have here is that somehow this logic doesn't work for linear algebra. It doesn't allow expressing linear algebra. Well, the research direction was, let's try to introduce more to this logic so we can express linear algebra and maybe we can get a logic for P and all this stuff. So for instance, we can introduce counting quantifiers, meaning that we can claim that there are 25 elements witnessing something, for instance. Not enough. We still can express matrix rank. Okay, let's add computing matrix rank operator to our logic. Well, for a while, it was kind of hoped that that may be enough. No, just 2 years or 3 years ago, a counterexample was constructed. This is not enough again. So now we're thinking, what else can we add? Okay. Another one is the valued CSPs, which basically the question is, well, can we optimize something here? So far we are talking about, does it have a solution or not? Can we optimize? Of course we can. So for instance, we are given a bunch of constraints. We may want to satisfy as many as possible or unsatisfy as few as possible. Well, it's not the same if you want to approximate, right? Well, in that case, the problems are known as max CSP and min CSP. We can use valued CSPs. For instance, instead of predicates, meaning that, okay, well, our tuple of values belongs to the relation or it doesn't, we can ask, well, okay, well, if I have those values, maybe I can compute a function of those values. And then what I want, say, I want to minimize the total value of those functions or maximize the total value of those functions on an assignment, something like this. So that allows for optimization. And again, well, people have been working a lot in this area. And there have been several results, most notable of which is that what we need here is linear programming. So if we want to solve CSPs, the best algorithm is linear programming. Well, valued CSPs, max CSP. Linear programming, or maybe linear programming and whatever algorithm we have for decision CSP. So that's probably the most interesting lesson from here. Okay, a little bit more approximation. Well, if you work in kind of this theoretical abstract approximation, you cannot get away from the CSP because the fundamental problem there is the unique games, right? Again, well, as I showed before, right? It is conjectured, and Subhash actually got this Nevanlina prize just for a conjecture, not a resolution of a conjecture. In a games conjecture that basically says that such CSPs or max CSPs are absolutely impossible to approximate. So that's in a nutshell what unique games conjecture is. And it's a CSP. And it's in the core of all approximation these days, like abstract approximations these days. Okay. If we assume this conjecture, then again, it turns out that all these CSPs can be well, the best way to approximate them is to use semi-definite programming. Again, just a single unique algorithm to rule them all. Okay, and well, there is a lot of other stuff. Like, well, in this conference, there was this talk about social choice, Arrow's theorem, and things like that. Well, an interesting thing is that actually the theorem itself can be stated and proved using CSP techniques. Well, not CSP itself, but CSP techniques. And, well, many other areas are related to, well, this kind of CSPs as well. Okay, so what do we do? Let's get to the result finally, and I probably have a few minutes to do that. So let's look at the CSP again. This is our definition. What we often do, we say, okay, we cannot use just arbitrary relations here. Right? I want to specify very carefully pick relations I'm allowed to use. In this case, it's known as a non-uniform CSP, well, a bad choice of a term, but anyway. So suppose that I am only allowed to choose those relations from some set gamma. Okay, if this is the case, then, well, the problem I get is denoted CSP of gamma. And this is what I'm going to talk about now, mainly. Okay, so examples. Graph K colorability. If you remember how we define it, we only use this disequality relation and nothing else. So that's a CSP of disequality. Okay. What about 3 satisfiability? We only use those clauses. And if you think about that again, every clause is just a relation, ternary relation, 3 coordinates, right? And there are only 8 of them. Okay. Okay. Linear equations. Again, well, okay, here I should be careful. I want to limit the number of variables per equation. Otherwise, it's kind of a little bit wild. But anyway, if I do that, then, well, it's a CSP again of all relations that can be expressed by a single linear equation. Okay, 2SAT. Well, it's basically the same as here. Well, in this case, clauses are shorter, just 2 literals, so relations are going to be binary. H coloring. Well, that's easy. If it's a graph, that's just a CSP of this edge relation of the graph. Okay. Spatial reasoning. Remember this guy hiding behind a cupboard, right? So that's a CSP of all kinds of relations like this: behind, left, from, left to, right to, and so on and so forth. Allen's algebra. Well, same thing. It's a CSP of those relations: starts, during, etc., etc. What about Sudoku? Probably can spend like 10 seconds for you to think about Sudoku. Can we represent it this way? Well, unfortunately not. Because, well, Sudoku is a little bit too structured, right? I want to say, okay, I have these equalities, of course, but it's kind of very structured, right? These equalities should be this way, that way, and so on. While in general, well, I'm allowed to do it anyway, right? In any possible way. So Sudoku is a little bit more restrictive. So it's easier than a real CSP. Okay, so what would we like to know about those non-uniform CSPs? Of course, we want a complexity classification and algorithms wherever possible. So we want for every gamma, find the complexity and the solution algorithm for CSP of gamma. So in this talk, we're only talking about relations on a finite set. Finite. Infinite is a totally different ball game, right? So that's much really different. Anyway, so this is what we want to do. Well, a while ago, now it's what, 30 years ago, right? Feder-Vardi posed this dichotomy conjecture that we have a complexity dichotomy for CSP of gamma. Right? That every such problem is either solvable in polynomial time or is NP-complete. Okay? Right? So why would it be so? Why should we believe that? Well, if we look at examples, well, these are our examples, if you remember, right? So some of them at least. I didn't include spatial reasoning and Allen's algebra because they are all infinite sets. And I promise that there will be no infinite sets. So if we look at that, okay, graph K colorability tends to be NP-complete, unless K equals 2, which is kind of too easy. Okay, linear equations, 2-sat, solvable in polynomial time, tractable. For H coloring, well, things are a little bit more complicated, but anyway, well, it's solvable in polynomial time if and only if the graph is bipartite. And that's it. Okay, so we have solvable in polynomial time and P-complete. Well, either this or that. But in any case, this is what we have. And that's what Feder-Vardi knew when posing their conjecture. Okay, so to actually state the result, I will need one more definition, which is a little bit more technical than what we've seen before. I need to talk about invariance and polymorphisms. So suppose I have a relation, right? Imagine tuples, right? Tuples. And I have an operation. Right? So operation means that's a function, I have several inputs, and I compute the output. I say that f is a polymorphism of my relation if, okay, I have my relation with tuples, I take those tuples, apply my function, right, component-wise, I get another tuple, and this tuple must be in the relation as well. So in a way, f preserves the relation, So a simple example, let's take a relation that is expressible as a system of linear equations, right? Over some ring field, whatever field, right? This means that I can represent my relation as a system of linear equations, right? So this is the matrix of the equation of the system. Well, that's this right-hand side. So that's a system of linear equations. If my vector satisfies this equality, it belongs to my relation, right? If and only. Okay, I claim that this operation, x minus y plus z, is a polymorphism of this. What should I do? I should do the following. I need to take, well, it has 3 inputs, x, y, z. So I need to take 3 tuples from my relation, x, y, and z from the relation, right? What does it mean they belong to the relation? The relation is defined using this system of linear equations. So there have to be solutions of this system. A times x, A times y, A times z have to give me b, all of them. Now, what do? I apply the function to those 3 tuples. Okay? So I apply function to those 3 tuples, so x minus y plus z, and I want to show that they still satisfy the system of linear equations. So I multiply, well, I plug it into the system here, right? I plug it into the system, So I multiply the matrix by this vector. So what do I get? AX minus AY plus AZ. Okay, fantastic. Now, since X is a solution here, this is B. Y is a solution of that system. This is B, and this is B as well. So B minus B plus B is B. Right? So if I combine my three solutions this way, I always get another solution of the same system. Okay, if you know linear algebra, you know this is true. Without computations like that, that's pretty easy. Okay. This means that X minus Y plus Z is a polymorphism of that relation. So that's an example. Okay, so what is the result now? What I've been talking about. Again, one more definition. I say that an operation is a weak near unanimity if it satisfies the following equations. If all of the arguments are the same except for one, so this near unanimity, right, that they are almost unanimous except for one, and I place this kind of special one in every possible position, I always get the same result. I always get the same result. If this is true, my operation is near unanimity, is weak near unanimity. Okay? So the conjecture has been for a long time that, well, CSP, well, it was stated in a different way, but anyway, that's equivalent. The CSP of gamma is solvable in polynomial time if and only if gamma has this very special polymorphism. Okay, otherwise it's NP complete. And well, the result is just this, that this is a theorem now. Right. Okay, so that's basically the result. A couple of words maybe about proofs and things. Well, not proofs maybe, but what kind of things we encounter here. So I probably have 2 minutes to prove it, right? Okay. So just a couple of remarks about that. Well, firstly, the hardness case when things are NP complete has been known for a long, long time. Okay. The algorithmic part, design an algorithm, that was the difficult part. So now it's, well, we now have two algorithms to solve that. Well, his and mine. Well, more may be coming, but anyway. So there are two major types of algorithms used for the constraint satisfaction problem. One is a local propagation. So what does it mean? Say you have two constraints, right? Like say in graph coloring you have two edges, and suppose they overlap. Right? And then you say, okay, well, the first constraint tells me that the color green is not available for this second vertex. Right? This means that I can ignore every tuple here that ends with green. Because it's unavailable, right? Well, also this relation allows green, this one doesn't, and therefore, okay, it's kind of useless. I can remove it. This is what local propagation is. So I do that, I remove something, I try something else again, and maybe I will kind of reduce those domains and relations more and more. So that's local consistency. Again, well, we know a lot about local consistency. In particular, we know when a CSP of gamma is just solved by those algorithms, local consistency algorithms. Well, solved means that if I establish this local consistency, if I don't run out of values for my variables, it has a solution. Okay, right? The second class of algorithms is some sort of generalized Gaussian elimination, right? So solving linear equations, but on steroids, in a way. Again, we have a very precise algebraic characterization when that happens. Well, I don't want to go into details, but anyway. So in a nutshell, the theorem from the previous slide tells us that if we have any non-trivial polymorphism, any non-trivial symmetry of our language, then we have this weak W and U, weak near unanimity one. And therefore we can solve the problem efficiently. So symmetries imply easiness, imply algorithms somehow. No symmetries, no algorithm. Okay, so hopefully Dima will add something tomorrow. But for now, thank you.
Thank you, Professor. A very interesting talk. Does anyone have any questions? Any questions? I have a question.
Okay.
Does this work can be applied in the field of machine learning?
Machine learning. Okay, so what is a neural network, right? Well, it's a bunch of those functions that are computed locally, but then you compute things globally, right? So it's a CSP, for sure.
Any questions? Okay. Let's end here. Let's thank Professor Bulatov again. Now we can take a break for about 30 minutes. We will start again at 14:45.